All right.
Thanks.
Okay.
Keep
Hi,
it on that
everybody.
note.
Thanks for having me, first of all. And apologies for my English. It's not my main language. I have two kids, grown-up kids, both living in the UK, and they uh, keep saying that my English is terrible. So I hope you can survive it. And yeah, if I stumble, just let me know. I'll try to make myself more clear. If there is anything, just ask. First of all, like maybe a couple of things about myself. Uh, I first of all, I started working on and enjoying electronics when I was very young, like 12 years old. That is basically ages ago. And then also started programming when I was like 14. The first time I could put my hands on something that was programmable, and that was basically what I've been doing also for work ever since. So that's my passion, and I have other hobbies besides my work in both software and hardware. I'm an amateur radio operator. I like radios, and I do. My radio work is mostly CW these days. That is basically Morse code over the radio, because I like to do things that are, let's say, legacy. Also, I also like to go sailing. I have a small sailboat. That's why I'm also very interested in what Car is going to talk about later. And so I like the sea, and boating, and that brings also to what we are going to talk about tonight. And finally, I'm a pilot. I fly planes. So both I like to stay both very low above sea level and as high as possible. Okay. Um, Today we are going to talk about something we've done that is uh, really centered around Raspberry Pi, and it's about a large ship, relatively large yacht, actually, that I will introduce shortly. This Richard got in touch with me because it was published like last month and on the Raspberry Pi magazine. Um, and I like that because I think it's quite important to stress the fact that Raspberry Pi can also be used in quite complex and critical applications. It's not just a thing for like makers and hobbyists and whatever, although I firmly believe that the two things are very close. I don't like walls between the applications and fields and businesses and whatever. And the thing I really love about Raspberry Pi is that it's something that is deeply rooted also in the, let's say, maker uh, 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 philosophy and way of doing things, but also as a very solid ground in industrial applications. And what we're talking today is basically pretty much about that. Something that it could have been done very differently in a more, let's say, traditional way, and we decided to go Raspberry Pi very much. In fact, I basically have a company, actually two companies, that are built around Raspberry Pi. Raspberry Pi is basically the foundation of both at this time. Both companies were born before Raspberry Pi came up, but when Raspberry Pi became something that could be used for our business, it really made a difference. It was like a turning point. We really leveraged Raspberry Pi over the years, and what we're doing now probably would have not been the same without Raspberry Pi. But let's go. I don't have an actual presentation. I want to jump quickly to the actual thing and give you an overview and also take questions from you as we go. Just a few photos mostly. Let me share the screen. Okay. Hope you can see it. So what we're talking about is this thing. This is a tugboat that was built in 1962 in the UK, and it still has the British flag. It's a 250 tons tugboat. It's a pusher. That means basically, tugboats can basically pull ships or push them. This one is a pusher. That means that basically it goes again, basically touches the hull of the ship from with its bow that is very stiff and reinforced and can push large vessels, basically for maneuvering in ports and stuff like that. This thing was again built in 1962. It worked as a tugboat until I think the 80s. Then it was mostly abandoned until it was basically rescued about 10 years ago by a private owner who was fascinated with the history of the boat. It's really beautiful, actually, and he wanted to make a yacht out of it. So but keeping basically the heritage, the layout of the interiors is preserved, although of course it's very different from what the original tugboat was. It's a really nice boat. It's based in Italy now, and you can see here a few photos. It actually is bigger than what it looks like in photos. That's it. It's called Baltic, by the way, Baltic, and that's a photo of it from my boat in out at sea that we rendezvous a few years ago. And it was based in Liguria, just for like a couple of photos of the area. Liguria basically is on the north west side of Italy in the Mediterranean. Those are the typical, let's say, small towns along the coastline. The boat was based in Imperia, which is an fairly large city, not too far from the French border. That's an interior view, the view of the Imperia city from the port where the boat was based. So the view outside is pretty nice. And the view inside, as you can see, that's basically the deck of the boat. What you can see on the left side is basically the main touchscreen interface for both navigation and control of all the systems. On the right side is a different layout that was basically rebuilt like a couple of years later. A boat like this is pretty complex. It basically has all the complexity of a large ship on a smaller scale, smaller size. But the systems are pretty complex. It's heavy stuff in terms of power, mostly like the electrical distribution system is quite complex. It's not like a house, it's more like a factory. Okay. Um, and this is the interior of the engine room, the main engine room, um, and control racks, electronics racks. A problem is that it's not very big. It's like 25 meters, more or less. So it's and the technology is quite cramped. It's so the for example the fact that we have the main electronic racks inside the engine room is not good. It looks good, but it's really bad because the engine room when this thing is out at sea is basically sealed, is closed. There is of course a lot of ventilation, but the temperature inside the engine room goes very easily up to 50 or more degrees. Consider that even when the yacht is not going, so the propulsion is stopped. There is always this big, you see these big, let's say, things in the foreground. This is basically a generator, and this is an like 8 kilowatts generator. There are two of these plus another one that is like a 30 kilowatts that they call the small generator. It's not that small to me, that is used only like at night when the loads is relatively low. So there are always engines running, and the engine room temperature basically skyrockets in the summer. And this is the environment where we have all those, let's say, poor Raspberry Pis running. It's not a very, let's say, forgiving environment. Um, like, okay, here you have another couple of more photos, let's say, of one of the control racks. You can see a lot of those units on the top. You can see the logo is IONO, uh, IONO. The IO stands for input output, and those are like modules that do what they do is like input output modules, analog and digital. They control. It's a low level interface to a lot of stuff, and then we have a large number of Raspberry Pi based, compute module based small servers that do basically all the interfacing, like for NMIA, RS485, Modbus interface and stuff like that. Again, stop me if I say things that are not familiar to everybody. So it's a complex environment. I don't want to stay on photos, and I don't have big diagrams because I want to jump to the actual interface. But that's just to give you an idea. These are were actually the Strato servers based on the traditional Raspberry Pi Model B. Actually, they were Raspberry Pi 4 based, with a board from one of our boards on top of that in a single package. We will talk later about that. Well, here there's now, okay, these are links for the end, where you can go look at the different products. So let me go back to the actual interface of the Baltic. Okay, this is the main page. This is live. The boat, the Baltic is now in Civitavecchia. It's close to Rome, where it's spending, let's say, the winter time. It's basically mostly idle. but it's always powered, and many things are running on it. The Okay, I think the key thing maybe where we can start from is this one. Okay. Um, what you have here is basically what we can see here is basically the networking diagram of the technology that we have here. You can see here basically the key parts are these two units that we call HPsycho master and slave. HPsycho is the software, the application software that runs all this. It's a distributed architecture where we have several units, several processors doing different things. That's both for, let's say, sharing the load, and most importantly, reliability. So if components fail for any reason, components themselves, or like the servers themselves, or like the networking, there are many things for the power. Many things can fail. If anything fails, the failure is either, let's say, fully redundant, and can be recovered by a redundant unit, or the failure is partial. The idea is to try to avoid a full failure, basically, of all the control and supervision features. Um, and So that's why you say these. You can see these two things, like the main unit and the slave unit, because the slave is this is a fault tolerant, redundant architecture based on two fully independent servers. And if the master fails, the slave can't take over. There's more to that. Okay, but I will get to that in a moment. Um, these are the main servers. Then we have 1, 2, 3, 4, 5 other servers which interface to other subsystems, like going from the top to the bottom, like the fire alarm system, which is very critical for safety. The engine, the rudder part, the rudders, engine again. It's basically two different units. HVAC for like heating and cooling. And then there are like a number of other units that are basically the I/O modules that interface the different subsystems at the low level. On top of that, we have these 6 units here, which are basically room control units that are spread along the yacht, and they do basically many things like monitoring the temperature, humidity, presence. They work as intrusion detection, and these are all based on Raspberry Pi compute modules. So in total, we have like 1, 2 plus 6, 8, 9, 10, 11, 12, 13 Raspberry Pi units, mostly compute modules, installed on this boat, and they basically do pretty much everything. Staying on the user interface, as you can see here, basically this is the main page of the ship, from here you go basically everywhere. This is all done by Raspberry Pi, by the Raspberry Pi servers. This is probably one of the interesting parts. This is the electrical generation and distribution architecture. It's based on 3 generators. We have a two main generators. These are the port and starboard generators, 80 kilowatts each. There is a smaller night generator, as I said before, and there is the shore mains where we are now connected. So as you can see, there is basically an electrical distribution bus that's redundant. So each of the generators have basically two ports for the two buses. This is to prevent basically failures that could cause a total blackout of the whole unit. This would be also very dangerous, not only very inconvenient, but also very dangerous, because there is a lot of stuff that depends on electricity to run, like the rudders, the forward propellers that are used to steer in port. These are all electrical. So electricity is a critical part of the safety of the boat. And everything is controlled by this interface and the Raspberry Pis behind the interface and the software. Of course, there is also a total manual control based on like switches, but that is super inconvenient. It's basically a very, very last resort in case of a, let's say, total failure of everything. But it's something that we desperately try to avoid. In fact, one of the interesting things is that these different power sources can be paralleled, and you can switch from one source to another without a hard switch that would cause a momentary blackout of the main power. So one interesting thing is that, like, for example, now we are on shore mains. We could switch to generators, to the internal generators, and the way it would work is that the generators would be turned on, go up to speed, start generating electricity. The generator would then be synchronized to the shore mains. We have the electrical distribution is three-phase, 380 volts, 50 hertz. It would go in phase with the shore mains, and when it's in phase, these basically big breakers would basically close. The two power sources would go in parallel, and after that, the shore mains would be cut off. And so we would switch from one power source to another without a blackout, basically. You can just as well parallel the generators, and this can be done from here. Basically, I could click here, generator source. I'm not sure if you can see the cursor, but I could click generator source, and this would basically, in a few seconds, the generators would go on and do all that I said. Basically, with parallel generators and then disconnect the shore mains. I could also turn on physically the generator's engine, check all the data from the engine for monitoring and recording. This is also very important, both for safety and other aspects. And basically, so yeah, I have access to pretty much everything, as you can see here. So this is not, let's say, this is not a toy. It's a quite complex unit, and its reliability is very, very important for, let's say, the safety and comfort of everybody, all the people on board. Besides that, we have going from the top, of course, that's the basically main fuel. It has two main tanks, 15,000 liters each, and and what you see here on the bottom part of the screen is called Alpha Laval. Is basically a system that takes the basically fuel from the main tanks, and it's called Laval because it washes it. Basically, there is a centrifuge that washes the fuel to make it to be sure that it's clean, and from that you can safely feed the engines. So the main tanks don't feed the engines directly. This system basically takes the fuel from the main engine, from the main tanks, and feeds to these smaller tanks, relatively small, 7,000 and 3,000 liters each, and from these the main engines are fed. Then we have navigation, like this. Okay, this is the wind navigation data and everything. That's again real time, and all the alarms. There are basically hundreds of different alarms, and so a large log of all the alarms of everything happening, because it's a complex system. So when there are alarms happening all the time, when something goes wrong, it's super important for the crew to know the sequence of how things happened. Because this is critical to understand what's the source of the alarm. Otherwise, it will be super complex to figure out, troubleshoot, and fix the problems. Engine controls. It's basically you cannot actually let's say control the engine, but you have full monitoring of the engines from here. Oh, here there is maybe a nice story I can tell. So at the beginning there was no let's say interface to the engine parameters. That was the beginning. So we could only know that the engines were either running or not running. But we needed to integrate basically engines data in the supervision system. And so we asked the engine manufacturer, it's MAN, MAN, for an interface to collect the data from the engines and integrate that into the supervision system. That was, of course, it is available. It's possible to do that. The interface cost more than 10,000 euros each. So it's two, because we have two engines here. So it was like 20,000 euros to integrate the engines. In the end, we decided to do it, let's say, by ourselves. So we have a couple of our I/O units collecting data directly from the engine sensors, and that basically turned, and again based on Raspberry Pi, and that turned the cost from more than 10,000 euros per engine to 500 or 600 euros per engine overall. And this is where we get all the data from. Then we have the cameras. Sorry, it's basically, there's a trash can sitting on top of one of the generators. Yeah. Okay, these are basically inverters, chargers. This is the night generator here, and a nice trash can on top of it. This is the rudder room. Okay, the engine room is here. You can see these are the main engines, generators, big generators, tanks, big tanks in the middle. These are mufflers for the exhaust, so that basically to reduce the noise of the engine when the unit is running on engines. This is another view. These are the control racks, big generator, and the engine again behind it. And well, external view of the boat, bow and stern. Okay. We have lots of pumps, controls, many things. Everything, basically everything is controlled from this interface. Fire sensors monitoring, intrusion detection. Well, okay, yeah, I need the password to get into that. External lights, HVAC need to run because otherwise we're going to be late. The gangway is also controlled from here. I can raise, lower, extend, retract, and have a camera to watch it. Logs, manuals, again, yeah, networking, as we already saw it. All the status of all the I/O interfaces, and a lot of configuration pages. That does make sense to go in the details. So let's quickly look. Oh, so okay, so this is a big thing. I also have my small boat that is running on something similar. I can show you, but I won't spend time on this. Okay, this is it. It's a small sailboat, but the architecture is very similar. It's pretty much the same. Of course, everything else is super simple, but the core features are exactly the same. So it's a different interface running on a much smaller scale, but the hardware is very similar. So this is based on these kind of products. The main servers are what we call Strato Pimax. For the names, just a quick note on where these names come from. So the name of my company is Sfera Labs. Now, Sfera is the Italian word for sphere, okay? And we have 3 product lines: Strato, Iono, and Exo. Now, if you combine Strato with sphere, it's like stratosphere, then you have ionosphere and exosphere. Okay, so these are where the names come from. Strato is basically edge servers. So the main servers that we have seen on the Baltic run on this thing that's called Strato Pimax. It's a modular compute module based unit that has basically up to 4 internal expansion slots. You can see here. These are basically I/O boards or communication expansion slots that we can fit into the unit. I don't want to go too much in the details, but the key thing is that the core of this is Raspberry Pi, plain and simple. It's actually based on the compute module. The ones on the Baltic run on compute module 5, so they're very powerful. Strato Pimax also has an RP2040 microcontroller for all the housekeeping, let's say, reliability features like watchdog and switching from the main storage to a failover storage in case there is a failure of let's say of the file system on the main storage unit. I don't want to go into the details. You can go look at these, but again, reliability is super important here. So there are a number of features on Strato that are designed to make this unit work, even if at least part of it fails. And if everything fails, we have a redundant unit that takes over automatically. One thing I didn't mention about power. So these units are powered by the main DC power rail of yacht of the Baltic. This is a 28 volts power rail with a lot of batteries for backup. So basically, even if you turn off all the generators, the Baltic can go on for like several hours on batteries only. The downside of that, so we have a very reliable DC power source on one side. On the other side, this power source is incredibly variable and incredibly noisy. So when the generators and the battery chargers are up and running, you are very close to 30 volts. When the batteries are running only, you go down to 22, 23, depends. And in general, the power source is super noisy. If you look with an oscilloscope on the main rail, the noise is terrible. There are basically, I don't know how many electric motors or pumps and ventilation, HVAC, all these things. The amount of electrical noise in the boat is incredible. We have a large number of Modbus, so RS-485 buses running on the boat, and the Strato has a number of isolated interfaces trying to reduce, let's say, the impact of electrical noise, but it's really a tough, let's say, environment. So this is basically the Strato, the core unit. As you see, it runs on the compute module. The great thing is that we have a standard Linux environment. It's not a traditional PLC. It's super easy to work on that, and this is where basically the HPsycho software that is the key of what you saw is running on top. One thing I want to show you about this is this. So this thing, I can do this. We are in the basically let's say, technical interface of the supervision system. Okay, this is what I want to show you. Okay, if you look at this page, this log, basically this is what basically the data that is flowing that is being collected in real time from the different systems. Now the boat is now idling in port. Most of its systems are off. So, and these are all basically what we call events that are happening, and basically that the software running on the Raspberry Pi 5 is collecting, storing, monitoring to generate alarms, to show the data on the user interface. There are like 30, 40 events per second coming from the field when the unit is idling here, with propulsion off, generators off, navigation mostly standby. When the thing is running, it increases the amount of, let's say, data increases 5 to 10-fold. And Raspberry Pi 5 is able to take care of that quite easily. We have, you can see, yeah, about now it's all 4,500 data points that are the different basically values that you saw moving in the log, and all of this in real time. That's the CPU of the Raspberry Pi. It's busy at 14%. And the load average is around 0.4. When the thing is sailing, running on engines and everything is on, the load goes to about 25%, more or less. Okay, this gives you an idea of how powerful the Raspberry Pi 5 is. With Raspberry Pi 4, it would be about 3 times higher than this. So the CPU load would be like 60 or 70%. Load average would be more than 1. I know that because up to last year it was running on Raspberry Pi 4. Now it's running on Raspberry Pi 5, and that's what we have. So this is the core unit. Then we have, that's also interesting, a number of I/O modules that you saw in the main rack. Some are based on again on the Raspberry Pi CPU. Again, the compute module 4S in this case, and this is what we call Iono Pi Max. It's a fairly bigger unit with lots of quality I/O. And then we have other modules which are based on either Arduino or the RP2040 microcontroller from Raspberry with relays, digital and analog inputs and outputs, and all this kind of stuff. So it's a lot of hardware, as I said, and the good thing is that here we have like a distributed logic. So critical things that have to happen like at the low level, the logic is on the module itself. So not necessarily on the central processor. This is again to retain functionality and control even if there is a failure. We don't want to have a single point of failure if possible. That's the core, let's say, concept of the whole architecture in this kind of applications. And yeah, I don't have time, or I don't want to go into the details of the software side, but it's basically developed by us. It's called HPsycho. It's a pretty hard to pronounce name. And it's built in Java and runs on any Linux machine. And that's where we started, as I said at the beginning, just to close up this quick introduction. The reason why we started using Raspberry Pi is that many years ago we were basically running HPsycho on industrial PCs, again running Linux. When Raspberry Pi came out, we saw the opportunity to initially develop basically a scaled down hardware platform to run our software. And that's how we started using Raspberry Pi. So at the beginning, the Raspberry Pi was just a Raspberry Pi powered with a USB power supply. We used a medical power supply that was, let's say, reasonably reliable. But we very quickly realized that we needed something more in terms of hardware around the Raspberry Pi to make it, let's say, suitable to be used in this kind of applications. There are applications that run 24/7. They need reliability. They need to be pretty robust. So we started developing our own hardware to, let's say, wrap the Raspberry Pi into, let's say, a hardened, let's say, shell, providing things like power, interfaces, I/O, a watchdog, real-time clock, many other features, and that's how it started. The hardware development of Raspberry Pi around Raspberry Pi started because we had the need to run our software on a low cost but very reliable hardware platform, and that's how we started. We started basically because we had the need to do that, to run our own software. Basically these evolved into Sphera Labs because we we said, well, if it's interesting and useful to us, it could be interesting to others. And that's how we started basically creating these products. That is what you now see, on SphereApps. That's why I said at the beginning that Raspberry Pi was, let's say, a pivotal moment, a turning point in our evolution. And just to give you an idea, as I said at the beginning, it was industrial PCs. Now all of our hardware is based on Raspberry Pi. We completely abandoned, let's say, the Intel-based hardware architectures and are solely running on Raspberry Pi, whether it's the CPU for full stack software or the RP series microcontrollers for level applications. So I think I run long. I'm not sure, but if you have any questions, I'm here. I think yeah. Anything?
Thanks very much. That was it's really interesting. I did have a few questions, probably too many actually. So I guess I was wondering, what's Raspberry Pi to work? How are they to work with when you're trying to like develop your own kit like this? Do they have like a special department that's set up to help people like you, or
Yeah.
how does that work?
Yeah, well, it works in a very, let's say, friendly way for us. When we started, I have to say, we started working on this, like SphereLabs is now 7 or 8 years old. So we started working at this at the very, very beginning. Now there are many different products based that are basically that aim at using Raspberry Pi in industrial applications. There is Revolution Pi. There are many other products and companies doing something similar to what we do. But we were at the very early stages, so the interaction with the people at Raspberry Pi in Cambridge was very, very close and personal. So from Eben down to all the engineering team, we've been always, let's say, in touch. I have to say that because the Raspberry, and this is a really, really strong point for Raspberry Pi, because the Raspberry Pi is so well known, there was not really a lot of, let's say, need from our side to get help from them directly. We were basically, we could do basically most of the things on our own. We really didn't need or depend on support or help from Raspberry Pi, particularly at the beginning. We had that help. We could access them. I mean, I was in Cambridge like 3 weeks ago. We go there regularly. We talk regularly, but in reality, we don't need much. I don't know if it may look strange, but because the Raspberry Pi architecture is so well known, I can say open, not in the sense that the design is open. It's of course proprietary and protected, but everything about Raspberry Pi is so well known that basically we normally don't need much or anything. What we need, what is important for us, and what we get help from them that is not visible, let's say, in general, is the fact that we discuss like new products at very early stage before they are introduced, because the development cycle for our products is very long. Like to design an industrial product, do all the testing, compliance testing, blah blah blah. It takes a long time. Like for us, the design cycle is between 1 and 2 years of a new product. So we need to know. Sometimes we start designing a product on some Raspberry Pi parts that are not yet in the market. Okay, so we need to know this very well in advance, and this is where we have a direct relationship that is super beneficial fun and interesting, I have to say. But besides that, to develop stuff on Raspberry Pi products that are already in the market, we don't need much, actually. Although
Right.
Raspberry Pi is moving and they do a lot of things trying to help integrators, let's say designers, to develop things on Raspberry Pi. And they will do more in the future in a more, let's say, structured way, I would say. But the great thing is that they're pretty open and helpful.
Right. Another question I had is about the cooling. Like, are these devices passively cooled, or are they fan cooled, or how do you?
Both. Some are passively cooled, some are actively cooled. They have like StratoPi Max has a fan, a small fan. The fan is not really used to, let's say, take fresh air from the outside, but it's just to circulate air inside the main enclosure. With Raspberry Pi, we also use a heat sink on top of the Raspberry Pi. It's actually the standard Raspberry Pi heat sink. The fan is not the Raspberry Pi traditional standard one, let's say the one they designed, but it's our own. I don't know if I have a photo here. Yeah, no. It's inside. It's a small fan, vertical, that basically blows air into the along the heat sink and keeps the temperatures really nice, actually. And as I said at the beginning, the temperature in the engine room can become really problematic. Like 40 to 50 degrees inside the racks is possible in summer in particular. Now in winter is not so much so. Let's see. Now we have. Let's see if. Okay. Where there's the temperature somewhere. Remember the time. I wanted to find an actual temperature, but anyways, it's in the unit. It can be like 30 degrees, 30 to 40 degrees. Now that the temperature is probably internal temperature in the engine room is around. Oh no, here it is. Okay. Okay, here we go. The temperature now is 17.5 degrees in the racks, and the server temperature inside the StratoPi Max is 47, 48. It gets warmer up to 60 to 70 in the summer when the engines are running. So with Raspberry Pi 5, you really need active cooling. With Raspberry Pi 4, maybe not so much. Actually, the Raspberry Pi 5 is not, let's say, warmer than Raspberry Pi 4. If you make it run at with the same performance level, the Raspberry Pi 5 can actually be cooler than Raspberry Pi 4. But if you push it, it gets very, very warm.
Right. Okay. Carl, did you have a question?
I was just asking how many Raspberry Pis on the ship. That's you asking for me.
Did you hear that question?
No, sorry.
How many Raspberry Pis on the ship?
Okay, yeah, about 13 or 14 at this time.
Oh, okay. I got the impression it was hundreds from that description.
No. Actually, yeah, as you can see from here, basically the everything what you saw basically runs on this main unit. Okay, here. The slave is a failover unit. It is in standby. It basically does everything that the master does. It shadows the master, basically. Okay, and it's ready to take over if the master fails. If it goes offline, the slave takes over. You would not see basically any difference, just a yellow line on the side here, the side of the menu. On the user interface, everything would keep working as normally. And then you have these units here, the 1, 2, 3, 4, 5 to the right side of the screen, that are basically Raspberry Pi compute module based units to interface everything else. On top of that,
Okay.
you have around 15 or 20 direct I/O modules that work at a very low level, and these are based on the RP2040, and some of them are based on Arduino, because when we started with this boat, the RP2040 was not yet available, but they are functionally identical.
Thank you, thank you, Ulrico. That's very impressive. I'm amazed by all that wiring and everything. There's quite a few other questions, so I'll duck out. That's a good answer. Thank you.
So there's a question online about what you're using for mass storage. Do you have like an array of?
Yeah. The main storage is all on the main controllers, the master and slave, and it's SSD based. So it's super fast, so much faster than the micro SD, of course. It's an industrial. It's inside the Strato Pi Max. We have an M2 2242 slot for SSD. We use, of course, industrial grade SSD units from Swissbit in this case, about 500 gigabytes in size at the moment. Consider that we do basically most of the storage is used for video recording of. We have about 10 cameras, and they constantly record. And this is done it's not done on a network video recorder dedicated to that. It's done on the Strato Pi Max itself. Just to give you an idea of how much extra power we have on this thing. So we can afford to do all the actual low-level control with so many events that you saw before, and on top of that, we have let's say room to spare, so we can afford to do the video recording on the main controller itself, as you can see here. Basically, okay. So this is basically, yeah. See, this is basically, so it's constantly recording from all cameras. This is very important for the safety, like the engine room, for example. We had in the past issues like short circuits. So you see smoke coming out all of a sudden. You want to see, for example, when there is an alarm, you go look at the cameras and the recordings and see what's going on, what's happening, and whatever. This is all done on the main unit and stored on the SSD that we have based on Raspberry Pi 5.
Okay, there's more questions in the chat. I don't know if anyone wants to come off the mute and ask a question, or I'll just read them out.
Okay. I didn't look at the chat, honestly, so let me.
Yeah, that's fine.
Okay.
So there's
Okay.
about whether or not what OS you use and whether you customize it.
Okay. So the OS is the standard Raspberry OS. Standard Raspberry Pi OS. We just it's the let's say headless version. There is no UI on the server, so there's no HDMI video output or whatever. It's just basically headless unit with our software HPsycho running. It's basically the UI is web based, as you can see. This is a browser. Nothing more than that, so the OS is totally standard.
How do you upgrade your system? Like if you have to upgrade your software, you just log in and do that, or?
Oh yeah. Basically, from here, that's the main user interface. I can go here what we call file manager, and basically I could, let's say, upload the new version of the application software or the core HCycle software. What we do not upgrade, let's say, automatically is like the OS. Consider this thing is normally or can be and runs offline. It's not a cloud-based system or a home appliance that automatically upgrades and restarts when it wants. It has to be super stable. When we need to upgrade, basically normally it's done on the slave unit, then on the master. It's a very controlled process. But besides that, it's normal standard Raspberry OS, not a special, let's say, version of Linux. It's not real time. It's not a real time Linux. It's normal standard plain. Because again, if we have like real time needs, that's done on the I/O modules at a lower level or peripheral systems. This is mostly supervision. So it has to be able to keep pace with all the events coming. So it cannot lag behind. But it's not, let's say, critical in the sense that it needs to respond in 5 or 10 milliseconds to external events. If it responds in like in 100 milliseconds or 50,000, 50 milliseconds, it's fine. Then I see use redundant network switches or multiple paths. There is redundancy in the network, and there are spare units. We decided not to go for a fully redundant network because it would have had the like complexity that could have been problematic. Like because the switches are, let's say, fairly reliable normally. You don't expect them to fail. And again, if something fails, like a switch fails, it doesn't bring the whole thing down. Okay, it brings partial systems down. They of course have spares, and they know how to quickly replace the switches with a spare unit in just a matter of a few minutes. Okay, adding full network redundancy would have been possible, but it would have added complexity, and in some cases even increased the risk of failures. So it was the decision was not to make the networking fully redundant. Although we have, like, for example, low-level RS-485 buses where we basically carry most of the control things, which is not on the LAN, but on Modbus buses. Like the main controllers have fully redundant buses and fully redundant interfaces to the buses. So StratoPi is basically making Raspberry Pi industrial grade for complex automation systems like yachts, right? Yes. In this case, yes. What class of yachts typically use your systems? Well, again, as I said, this one is a 250 tons thing, 25 meters yacht, and my boat is a 37 feet sailboat. So it's basically, let's say, very scalable from small things to large ones. The SSDs we saw. Yeah, okay. I think these are pretty much all the questions that I see in the chat.
Great, thanks very much. Is there any questions in the room? Anyone? Yeah.
Thanks for the presentation. That was lovely. Quick question on, you mentioned on your redundant power supply, you had a lot of noise coming in from the systems that were plugged into it. How do you protect the Raspberry Pis from dirty power? And secondly, have you found, because obviously you've been running this now, you mentioned for 8 years, have you found that these systems have reduced the mean time before failure for any of the units?
Yeah. basically the first thing that we designed at the beginning when we started working with Raspberry Pi was like a pretty reliable power supply stage. So like StratoPi Max as well as IonoPi Max, they can be powered from anything like 9 to over 50 volts. The power supply accepts a lot of let's say fluctuations on the main rail. Like you can have the StratoPi Max perfectly running, let's say, on like at 12 volts, and then a moment later, ideally, it goes to 50 and then drops back. Everything keeps going nicely. It's very heavily filtered. We test all these, all the products are tested for like immunity standards in industrial environments. That is basically maximum, let's say, fairly substantial amount of let's say electrical disturbances coming from the outside. So we try to make these things reliable in this respect. We also have some things like that, like for example, can you see here this photo here? This is a supercapacitor based UPS unit that is inside the StratoPi Max. So it's even able to withstand like total drops of power supply for, in this case, like 30 to 60 seconds or 90 seconds. Or we have a UPS with an external battery, like those batteries that you see in burglar alarms and stuff like that, that they need to stay powered even if there is a power failure. So this part of the power supply is very, very critical and again, super important. The Raspberry Pi has always been very, I mean, even the normal Raspberry Pi, extremely reliable. And in many cases, when you hear about instability, file system corruption and stuff like that, in many cases it's related to the quality of the power supply stage. Of course, if the power supply stage is a USB wall-worked basically phone charger, you cannot expect much. And this thing is getting even worse because the things like Raspberry Pi 5, they have very, very variable load based on the CPU load. And so the power supply needs to be able to quickly respond to very, very changing loads very, very quickly to prevent voltage drops and stuff like that. They could have basically a lot of negative impact in terms of reliability. So the power supply is absolutely critical to the reliability of all this. Then we have other features, like for example, we have a watchdog that is completely external to the Raspberry Pi complete module. It's based on the RP2040. It monitors the CPU. If it fails to respond, if basically the heartbeat fails, the watchdog can completely not just reset, it turns off the Raspberry Pi CPU completely and restarts. It can also do other things like, for example, if we were talking about the file system, if the main file system fails, so if the Raspberry Pi is unable to boot from the main SSD storage, the watchdog will power off the Raspberry Pi, turn off the SSD storage subsystem, try to turn it on again. So it basically power cycles the SSD, because in some cases it can, let's say, restore and make it work again. Sometimes some SSD basically the let's say low cost units can even hang in some cases, like the controller inside the SSD can hang. And the watchdog in StratoPi Max can remove power to the SSD subsystem and repower it. If everything fails, it can keep the SSD subsystem off, so it doesn't interfere, doesn't prevent the Raspberry from booting, and then the Raspberry Pi would boot from either an SSD and a micro SD card or the internal eMMC storage, where the file where basically we have a failover file system on that mirrors basically the core part of the SSD unit. So we basically have redundancy in the main StratoPi Max unit, and on top of that, we also have a full redundant server in the high availability architecture that I was mentioning. That is basically on the software side.
Okay, thanks very much. Those are really
Oh, I don't have all these things on my boat. On my boat, for example, my small sailboat, I have just one IONO-Pi Max. In that case, it does everything. It's a single unit that does both the I/O and the processing. And the reliability, the redundancy I have is that in that case, it runs on micro SD cards, and I have 2 SD cards. And again, the watchdog can fail over between one and the other.
oh, okay. Well, thanks very much.
Another
That's-
question. I see another
No,
question.
we're gonna have to stop there.
Yeah, sure. Okay.